What if space and time are not real? You stretch out your hand, reaching for a glass of water. You feel the cool air between your skin and the glass. Your eyes estimate the distance. Your brain calculates the movement almost unconsciously. In a fraction of a second, your arm extends, your fingers curl, and you lift the glass. To you, it feels obvious, natural, even boring. There was space between you and the glass. There was time in the motion it took to reach it. Simple, ordinary, unquestionable. But what if I told you, this distance doesn't exist? That the time you just experienced isn't real? Think about that for a moment. Everything you've ever done, walking to school, traveling across continents, waiting for your birthday to come, even listening to me right now, depends on the existence of space and time. For thousands of years, humans assumed the answer was obvious. Philosophers like Aristotle described time as the measure of change. Space was the grand container in which all objects rested. To the naked eye, reality seemed structured, the earth beneath, the sky above, days unfolding in an endless rhythm. It felt so natural, so self-evident, that no one thought to question it. But then came the dreamers, the heretics, the thinkers who dared to whisper, "What if this isn't real?" Plato, centuries ago, described our existence as shadows dancing on the wall of a cave, illusions mistaken for truth. Centuries later, Einstein shattered the Newtonian certainty that space and time were absolute. He showed us that they could bend, stretch, even break under the weight of gravity and speed. Time slowed down near massive objects. Space curved like fabric around stars. Picture a heavy ball placed on a stretched rubber sheet. The sheet curves. The sheet curves. Smaller balls roll toward it, not because of some invisible pull, but because the surface beneath them is warped. This was Einstein's vision of the universe, stars, planets, and galaxies shaping the very fabric in which they existed. It was revolutionary. For the first time, we realized that space and time were alive, dynamic, flexible, sensitive to the presence of energy and mass. The closer you move to the speed of light, the slower your time runs compared to someone at rest. Near a black hole, time doesn't just slow, it practically freezes. Einstein's ideas were so bold that many doubted them, until 1919, when astronomer Arthur Eddington led an expedition to observe a solar eclipse. The results stunned the world. The sun's gravity had bent the light of distant stars, exactly as Einstein predicted. Overnight, Einstein became a global icon, and Newton's absolute stage crumbled. But just as humanity was beginning to adjust to this strange new cosmos, the quantum world arrived with its own revelations. Here, particles didn't respect the boundaries of space. They blinked in and out of existence, leaping across distance as if it were meaningless. Entangled particles acted as though space itself was irrelevant, instantly connected no matter how far apart they were. It was as if the universe was whispering to us, what you call space, what you call time, are not the bedrock of reality, but illusions, constructs of the human mind, tools we invented to make sense of something far stranger. Imagine looking at the ocean. You see the waves rising and falling, crashing against the shore. But the waves aren't the ocean, they're just patterns, temporary shapes created by deeper movements of water. What if space and time are like those waves? Not the ocean itself, but fleeting appearances, disguises for something more fundamental beneath. So let's return to that moment. You, reaching for a glass of water. You think you crossed space. You think a second of time passed. But what if what really happened was something else entirely? An unseen rearrangement of relationships, of information, of reality itself. Stay with me, because if space and time are not real, then what are we really living in? Part 2. Our story begins in the early 20th century, a time when science seemed almost complete. For more than 2 centuries, Isaac Newton's vision of the universe had reigned supreme. To Newton, space was a giant stage, absolute, infinite, unchanging. Time was the great cosmic clock, ticking steadily for everyone, everywhere, unaffected by motion or matter. The laws of physics were written upon this eternal canvas, and for generations it felt unshakable. But then came a quiet, unassuming clerk working in a Swiss patent office, Albert Einstein. In 1905, he began to unravel this grand certainty. With his special theory of relativity, Einstein revealed that time could slow down, and lengths could contract depending on how fast you moved. What Newton thought was absolute wasn't absolute at all. And then, in 1915, Einstein went further. His general theory of relativity painted an image so radical it shook the foundations of science. Space and time were not separate entities, but interwoven into a single fabric, spacetime. And gravity? It wasn't a force tugging across empty space. It was the very bending and warping of spacetime itself. Picture a heavy ball placed on a stretched rubber sheet. The sheet curves. Smaller balls roll toward it not because of some invisible pull, but because the surface beneath them is warped. This was Einstein's vision of the universe, stars, planets, and galaxies shaping the very fabric in which they existed. It was revolutionary. For the first time, we realized that space and time were alive, dynamic, flexible, sensitive to the presence of energy and mass. The closer you move to the speed of light, the slower your time runs compared to someone at rest. Near a black hole, time doesn't just slow, it practically freezes. Einstein's ideas were so bold that many doubted them, until 1919 when astronomer Arthur Eddington led an expedition to observe a solar eclipse. The results stunned the world. The sun's gravity had bent the light of distant stars exactly as Einstein predicted. But just as Einstein was redefining the cosmos, another revolution was brewing. One far stranger. Physicists studying the atom discovered a world that made no sense at all, the quantum world. Here, certainty dissolved into probabilities. Particles behaved like waves, then like solid matter, then like both at once. Electrons could be in two places at the same time, and particles could vanish and reappear as if space itself were just a suggestion. This was not Newton's tidy universe. It wasn't even Einstein's elegant space-time. This was something else, wild, unpredictable, surreal. And here's where the great puzzle began. Einstein's general relativity worked perfectly for the grand stage of the cosmos. Stars, galaxies, black holes. Quantum mechanics worked flawlessly for the tiny world of atoms and particles. But when scientists tried to combine them to describe the universe as a whole, something broke. The equations spiraled into infinities, contradictions, impossibilities. It was as if two different languages were describing the same reality, but neither could be translated into the other. This clash raised a haunting possibility. Maybe space and time aren't fundamental at all. Maybe they're just approximations, like the illusion of a rainbow, which disappears when you try to touch it. Maybe space-time is not the foundation of the universe, but a shadow of something deeper, more mysterious, more real. And that's where our story takes its most unsettling turn. In 1964, the world of physics was shaken by an experiment so strange, so counterintuitive, that it still haunts science to this day. Physicists John Bell and later Alain Aspect weren't just studying particles, they were testing the very structure of reality. Their target was one of the weirdest predictions of quantum mechanics, entanglement. So what is entanglement? Imagine creating two particles, let's say two photons, born together in a single quantum event. They are like twins, linked in ways invisible to us. You separate them. One stays on Earth, the other you send to the far side of the galaxy. And then, you measure one of them. Instantly, the other knows the result. Their states match, as if some invisible thread connects them across the universe. This was no theory. It was tested, retested, and confirmed. Alain Aspect's famous experiments in the 1980s finally proved what John Bell's theorem had suggested. Entanglement is real. But here's the catch. If space is real, if distance truly separates objects, then how can one particle affect another instantly, faster than the speed of light? No signal could possibly travel that quickly. According to Einstein's relativity, nothing in the universe can outrun light. Einstein himself hated this idea. He mockingly called it spooky action at a distance. To him, it was proof that quantum mechanics had to be incomplete, that there must be some hidden variables, some secret mechanism we didn't yet understand. But as experiments grew more precise, the verdict became unavoidable. Einstein was wrong. There were no hidden variables. Entanglement was not a trick, it was real. This left physicists with a chilling possibility. Maybe distance itself is an illusion. Maybe particles aren't really separated at all. Instead, they are part of the same underlying reality, connected in ways that transcend our familiar notions of space. Chapter 2. Time under attack. We experience it as a constant flow, a river that carries us from birth to death, from past to future, 1 second at a time. We celebrate birthdays because we feel time moving forward. We grow older because we see time leaving its marks on us. Everything in our lives seems bound to this current, relentless, unstoppable. But physics tells a different story. What did he mean? To Einstein, time wasn't something that flowed. It wasn't a universal tick-tock shared by everyone. Instead, time was woven together with space into space-time, a vast four-dimensional block. Within this block universe, the past, present, and future are all equally real. Think of it like a book. Every page already exists. Page 1 is the past. Page 2 is the present. Page 3 is the future. We, as conscious beings, flip through those pages one by one, believing the story is unfolding, when in truth, the whole book is already there. To the equations of physics, there is no now. The laws of motion don't highlight a single privileged moment. They don't care if you're talking about yesterday, today, or tomorrow. All of it, every memory, every possibility is already written into the structure of spacetime. But some thinkers have pushed this even further. British physicist Julian Barber argues that time itself may not exist at all. In his vision of timeless physics, what we call time is just our brain's way of organizing change. Imagine the universe as a vast gallery of frozen moments, snapshots of every configuration of matter. This raises a haunting question. If time doesn't flow, if it's just an illusion of perception, then what are we? Chapter 3. The Holographic Universe. In the 1990s, a radical new idea began to take root, an idea that would challenge the very meaning of reality itself. It was called the holographic principle. Physicist Juan Maldacena proposed something extraordinary, that our entire three-dimensional universe, including space, time, and everything in it, might not be fundamental at all. Instead, it could be a kind of projection, an image cast from a deeper two-dimensional reality. Think of a hologram on your credit card. To your eyes, it appears to have depth, layers, curves, a 3D structure, but touch it and you'll find it's flat. The depth is an illusion, a trick of light encoded in just 2 dimensions. Now imagine this same principle, not on a card, but applied to the entire universe. This astonishing idea didn't come out of nowhere. It grew from an even stranger mystery, black holes. In the 1970s, physicist Jacob Bekenstein made a shocking discovery. He found that the amount of information, or entropy, a black hole could hold was not proportional to its volume, as you might expect, but to the area of its surface. Later, Stephen Hawking confirmed this with his famous work on Hawking radiation. This suggested something profound, that the true content of a black hole wasn't inside it, but written on its surface. Maldacena took this insight and extended it to the entire universe. If it's true for black holes, he asked, why not reality itself? Maybe everything we call space and time emerges from a deeper two-dimensional framework. In this view, space is not a container where events happen. Time is not a flowing river. They are illusions, emergent properties created by the underlying code of reality. Chapter 4. Quantum Gravity and Emergence. Today, some of the most daring minds in physics are chasing what may be the ultimate prize, a theory of quantum gravity. The goal is simple in words, but monumental in scope: to reconcile Einstein's smooth, curved space-time with the jittering, probabilistic chaos of the quantum world. And in this quest, a radical new suspicion has emerged, that space-time itself is not fundamental, but emergent. What does that mean? Think of temperature. To us, it feels like a basic property of matter, warm, cold, hot. But in reality, temperature isn't fundamental at all. It's a collective effect, an average of trillions of molecules moving at different speeds. Zoom in far enough and temperature disappears. What's really there are just atoms in motion. Now apply that same logic to space-time. To our senses, space feels smooth and continuous. Time feels like a steady flow. But what if at the deepest level they don't exist as we know them? What if they are large-scale illusions, emerging from something far smaller and stranger, a hidden network of quantum relationships? Picture a glass of water. It looks calm, uniform, almost featureless. But under a microscope, you'd see a storm of molecules colliding, vibrating, interacting. The calm surface is just an illusion created by chaos beneath. In the same way, space-time might only appear continuous, an illusion created by the tangled dance of quantum entanglement. In fact, many physicists now suspect that space-time itself is woven out of quantum information. Entanglement, those mysterious links between particles, might not just be a weird feature of physics. It might be the stitching, the invisible thread that creates space and time. One of the boldest ideas in this field comes from Dutch physicist Erik Verlinde. Verlinde argues that even gravity, the force that shapes the planets, binds galaxies, and guides the destiny of stars, isn't fundamental. According to him, gravity is not a force in the traditional sense, but an entropic effect, a kind of statistical byproduct of information and entropy. Think of a rubber band snapping back when stretched. It's not pushed by a mysterious force, but by the collective tendency of its molecules to return to a more probable, more ordered state. If Verlinde is right, then what we experience as gravity, distance, and even time itself are not primal ingredients of reality. They are emergent illusions, born from the deeper flow of information. And that raises an even deeper question. If space and time are not the foundation of existence, then what is? But wait, what if all of this, the talk of illusions, holograms, and emergent realities, is simply our own misunderstanding? For centuries, humans have mistaken the limits of their knowledge for the limits of the universe. We once believed Earth was the center of creation. We once thought disease was caused by spirits, not microbes. Again and again, we've projected our ignorance onto the cosmos. So perhaps declaring space and time illusions is just another error born from the edges of our understanding. After all, our entire existence, our measurements, our experiences, even the story you're hearing right now, is structured within time and space. The rhythm of your heartbeat is measured in seconds. The distance between you and the screen in front of you is measured in space. To call them not real feels almost absurd. It risks dismissing the very fabric of the observable universe. And philosophers push back even harder. If space and time are illusions, then who or what is experiencing the illusion? If your mind is generating the sensation of here and now, doesn't that suggest consciousness itself exists outside of space and time? If so, what does that mean for us? Are our minds tapping into some deeper level of reality beyond the physical? And then comes the most unsettling possibility of all. What if space and time are real, but simply beyond our comprehension? Imagine an ant crawling across a painting. To the ant, the world is just patches of color beneath its feet. It cannot see the full picture, the faces, the landscapes, the story the art is telling. What if we are like that ant, trapped in a limited perspective, unable to perceive the true dimensions of space and time? Perhaps they are not illusions, but grander realities, layers of existence so vast, so alien, that human perception cannot grasp them. And here lies the haunting truth. Maybe the problem isn't that space and time are unreal. Maybe the problem is us. Our brains, our senses, our science are not yet advanced enough to touch the full scope of reality. Conclusion. So, what does all of this mean for us, for living, breathing humans bound to the ticking of our clocks and the distances we cross each day? It means reality may be far stranger, more interconnected, and more mysterious than we ever imagined. That when we look at the stars, or feel the seconds slipping away, we may be touching only the surface of something infinitely deeper. Perhaps, just like shadows dancing on a cave wall, space and time are projections, useful illusions that guide us but hide the true essence of reality. And so I'll leave you with this question. If space and time are not real, then what is real? Maybe the answer isn't out there in galaxies and equations. Maybe it lies within us, in the mystery of consciousness, in the act of questioning itself. Because every time we ask, what is reality? We are already peering beyond the veil.